Welcome to lesson 7.3. Today we're going to talk about logistic equations. Alright? Now, exponential growth is modeled by this particular solution, y equals c e to the kt, but that really assumes unlimited growth. So it goes on forever and ever and ever, and usually is quite unrealistic, right, for most populations. More typically, what happens is the growth rate decreases as the population grows, and there really is some sort of maximum population out there, M, called the carrying capacity. Now, when we have this little twist, we model it using something called the logistic differential equation, which is this: dp dt equals to k times p, where p is the population, times m minus p. Okay? Now, when you solve this differential equation, you don't get this one here anymore. Sorry, we get something different. And yes, it's listed here below. But I think what I'd like to do is actually show you this. So if you can go to the 7.3 supplement in the back of your book, yes, I want to just quickly review how to solve these differential equations and then show you how we can solve the logistic one. You ready? This is going to be fun. Okay? So as a quick review, can we solve this one? Yeah, I hope so. Separate the variables. Y will go on one side, and then the dt will go on the other side. Remember, k is a constant, right? So don't worry about that being another variable. We're going to take the antiderivative, which gives you the natural log of the absolute value of y, equals to kt plus c. I hope you remember we can take e to the both sides now to get just the regular absolute value of y. This becomes e to the kt plus c, which actually is e to the kt times e to the c. And once again, that absolute value with the e to the c just becomes a new constant. So y equals c e to the kt. Right? Easy. So now the question is, well, if the derivative is not proportional to the original function, which I think, like I said before, most things are not, how do we limit that growth? So we now change this differential equation to the following: dy dt equals to ky. Okay, we still have that, but we have now this limiting factor, which we call bracket m minus y, where m is the maximum amount, or what I said before, the carrying capacity. Okay? Now, our goal is to solve this equation: dy dt equals ky times m minus y. Now, this time here, we have two constants, the k value and the m value. Okay? Now, we still need to do the same thing. We need to separate the variables. So we need to bring everything with the y to the left side. And I'm going to see dy over y. Yes. Now, what about this m minus y? We can't break that up, so unfortunately, you're going to have to bring the whole thing down to the denominator of the left side. And my right-hand side still just becomes k times dt. Okay? Ho, 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 ho. Yes, we need to anti-differentiate. Ho, 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 ho. But the left side here, what technique do we have to use? Uh-huh. Partial fractions. That's right. Oh, gotta separate this into two fractions. A over y plus b over m minus y. Okay. And this must equal to 1 over y bracket m minus y. Now, I hope you remember how to solve partial fractions. We will multiply it by the terms, so a bracket m minus y, because we want to have the same denominator, plus b times y equals to 1. And once again, if you want to write down the denominator, you can. But why did we do this? Because now they all have the same denominator, and then we can just equate the numerator. Yeah. Now, how do we solve for a and b? You remember? Yeah, we can just use this math idea that we can say plug in y equals to m into the highlighted expression. So A equals to M, not equal to, A multiplied by M minus M plus B times M equals to 1. And then we can solve for B because Bm equals to 1 since that is 0. And B equals to 1 over M. Nice, nice, nice. Similarly, we do the same thing. This time I'll let y equals to 0 to help me get rid of the b. A times m equals to 1. So a equals to 1 over m. Look at that. It's the same thing. Nice. So knowing these constants now, I can plug them back in and then rewrite my differential equation. Sorry, not differential equation. My integral as the integral of 1 over m over y plus 1 over m over m minus y. This whole thing is dy, and then the antiderivative of k dt. Okay, so once again, all I've done is I've replaced that with this. Okay. Now, to make life a little bit easier, I think I'm going to factor out that 1 over m. So let's take it out, 1 over m. So that just is in the integral of 1 over y plus 1 over m minus y dy equals to integral of k dt. Okay? All right. I'm going to do now, well, I don't like that 1 over m in front of the integral on the left-hand side, so I'm going to move that to the right-hand side. I'm going to go integral of 1 over y plus 1 over m minus y dy equals to now the integral of m times k dt. Okay? Once again, m and k are constants. Now I'm going to move to the next page. So I hope you can turn to the next page too. I'm going to ask you to now do the antiderivative. So what is the antiderivative of 1 over y? You got it. Natural log of the absolute value of y. What is the antiderivative of 1 over m minus y? If you said plus natural log of m minus y, I'd be like, whoops. Remember that y has a coefficient of -1 in front. It's not a positive y, so I have to use chain rule or reverse chain rule to get rid of it. I need to, yeah, divide everything by -1. Okay. And just to finish off the right-hand side, mk is a constant, so the antiderivative is mkt plus c. Okay, now, once again, this -1 thing is what a lot of people forget, so let me just write it like the following. Natural log of the absolute value of y minus natural log of m minus y equals to mkt plus c. This is the correct antiderivative of the expression we had before. Now, you're not done yet because you need to actually solve for y. And to do that, I'm going to ask you to try to combine the laws together on the left-hand side. But I'm also going to do one little trick here to make life a little bit easier for us, and you'll see why in a second. I'm going to ask you now to just multiply everything by -1. Okay? Which means then this term becomes positive. I'm going to put that in front. Natural log of m minus y. Okay? And then this term here becomes negative, so minus natural log of y. And then this term mkt, of course, becomes negative. Plus c, well, you could make that negative c, but it's still a constant, so I'm just going to keep using plus c. Okay? Now, use your pre-calculus knowledge. Let's simplify this. Okay? Combining logs together, we get ln of m minus y over y now equals to negative mkt plus c. Okay? That's using log rules. Using log rules. I need to solve for y, so I need to get rid of that ln. I'll take e on both sides. So eing the ln, that just leaves me with m minus y over y in absolute value. And this is now e to the negative mkt plus c. Okay? And as I e both sides, remember I can now separate the right-hand side into e to the negative mkt times e to the c. And then I can combine that e to the c with the absolute value to make a brand new constant, which I'll just call c. So hello, m minus y over y equals to c e to the negative mkt. Whew. When you're thinking, how is that better? I still need to solve for y. Well, look. I can now separate the fraction on the left-hand side. M over y and y over y. Well, let me just rewrite that. Y over y is just, yeah, it's just 1. And of course, the right-hand side stays the same. That's nice, Cal, because now I can just solve for m over y, which just becomes 1 plus c e to the negative mkt. And you're like, but I want y, not m over y. I get it. So this is where I'm going to ask you, yes, to flip this or do the reciprocal y over m. And yes, I'm going to flip the entire right-hand side. And we're almost done because now I can solve for y. I'll just multiply both sides by m. So m goes on the top. 1 plus c equals, c times e to the negative mkt. And this, my friends, is the solution to the logistic differential equation. Okay? So just to quickly summarize, okay, the two things, and you're like, wow, that was a crazy thing. Do you mean I have to do this on the AP exam? No, you don't. Okay. My advice to you is if you're given this form, dy dt equals ky, automatically know that you get this equation, y equals c e to the negative kt, the exponential. Yet, if you're given this equation, dy dt equals ky times m minus y, this is the logistic one, then I'd ask you to memorize this. M all over 1 plus c e to the negative mkt. Okay? And this is the logistic, L-O-G-I-S-T-I-C, logistic equation. Okay? That is where that formula comes from. Now you know I wasn't lying to you. So going back to your notes, oh, look at that. Okay, so I didn't use y, I just used p, but whatever. P population, y population is m over 1 plus c e to the negative, and then instead of mkt, I just wrote kmt. Same thing, right? Okay. Just be aware though, unlike in exponential growth, c is not, do you hear me? Not the initial amount. Okay? So let's take a look at just one example, okay? Just one example, one huge example, okay? So let's look. It says a national park is capable of supporting no more than 100 grizzly bears, okay? And we modeled the equation with the logistic differential equation with this k value of 0.001. Okay, so let's write the differential equation first of all. So writing the differential equation, that means I want dp, okay, you can use dy if you want, but dp over dt, and that equals to what? K 0.001 y, or the p-value, times, yes, the carrying capacity, the maximum amount, which is 100 minus p. Boom. There you go. There's your differential equation. Now, it does say the slope field for this differential equation is shown to the right. Where does there appear to be a horizontal asymptote? And you think about it, looking right about here, you see how it kind of gets towards that 100? Yeah, I think 100, or when p, the population, equals to 100, you get a horizontal asymptote. Now, the question is, what happens if the starting point is above this asymptote? So over here, you see that? Yeah, the population decreases towards 100. And what happens if the starting point is below? Hmm. It looks like it goes and it increases. So the population increases toward 100. So now it says if the part begins with 10 bears, can you actually sketch the graph? So I better erase all the stuff. Ooh, erase, erase, erase. So now I'm saying if it begins with 10 pairs, so when t equals to 0, we are here at 10. Sketch a graph of p of t. So this is the original graph now, right? This is the not the differential equation, but the actual solution. So if I were to start to draw, I'm thinking, wee, and oh, something weird happened, right? Looks like it kind of changed. And as it moves, it gets flatter and flatter and probably gets towards, you got it, 100. Now, here I'd like you to solve this differential equation to find p of t with this initial condition. Okay, so let's try to solve this again. So really, this is the whole process I did before with you. Okay, taking dp dt equaling 0.001p bracket 100 minus p. And how do we solve this? Yep. You're thinking, no, we have to do partial fraction. Yep. Can't help you there. So just quickly here, I guess a over p plus b over 100 minus p is supposed to be equal to 1. P 100 minus p. So once again, cross multiply. And this time I'm going to speed up by just using the numerator. Okay, not ignoring the denominator because I know the denominator is going to be the same. It's just the p bracket 100 minus p. And then, yes, if I put p equals to 100, notice that the a becomes 0, so b times 100 equals to 1. So b is 1 over 100. And if I make p equals 0, you'll get the same thing for a, just like what I did before. A equals to 1 over 100. Okay? So instead of having that, I can now have the following. It will be 1 over 100 over p plus 1 over 100. 100 minus p. This is all dp because we're trying to do the antiderivative. 001 dt. And if we do that, I'll take out that 100, 1 over 100, right? I can move it to the other side. And really, I just get what? Can I do this in 2 steps? Well, I guess I better not. I'll try to show some more work. This one's pretty long. Okay. I'm going to take that 1 over 100 and stick it on the side. So that'll be 100 times 0.001, which just really equals to the integral of, I think, what, 0.1? Yeah, zero point 0.1 dt. And now I hope you're set to do this lovely integral. Here we go. Ln absolute value of p plus ln absolute value of 100 minus p equals to 0.1 t plus c. And oops, I made a mistake. Remember, this is not the positive sign because this is 100 minus p. That's right, reverse chain rule with the extra factor of a negative 1. So make that negative. Okay? I should highlight that. Make that negative. And then the trick that I showed you earlier was to multiply everything by negative 1. So that I can reverse this. So the natural log of 100 minus p minus the natural log of absolute value of p equals negative 0.1 t. And then once again minus c or just regular plus c. It's okay. All right. And then once again, we're going to combine it together. So natural log. Remember all this stuff we did? You're like, that's that whole proof again. I know. All right. Both sides. You're like, man, is this ever going to be done? It will be very soon. Trust me. To the negative 0.1 t plus c. Once again, that's to the negative 0.1 t times to the c with a lovely 100 minus p over p on the left-hand side. To the c in the absolute value to create this new constant. 100 minus p over p c to the negative 0.1 t. Wow. And then once again, we do that process of splitting it up. So yeah, I'm just doing that all over again. 100p minus 1, 100 over p equals 1 plus c to the negative 0.1t. We'll flip it. P over 100 equals to 1 over 1 plus c to the negative 0.1t. And then we will multiply by 100. And here's what we get. And then the only thing I need to do now is actually plug in this initial condition. Oh, what was my initial condition again? I totally forgot. Oh, right. If there were 10 bears at the beginning. So that means at the beginning, when time equals 0, I'm going to plug in the population is 10. 1 plus c to the 0. Thankfully, to the 0 is just 1. So this is what 10 equals to 100 over 1 plus c. We'll cross multiply. 10 bracket 1 plus c equals 100. 1 plus c equals actually 10. So c equals to 9. Yeah. Woo. All that work to get, whoops. You don't want to see that. All that work to get p equals to 100 all over 1 plus 9 to the negative 0.1t. There you go. Whew. Now, remember how I gave you that equation earlier? I said, yeah, you could have just forgot all that stuff and just memorized the equation. And if you did that, you just plug it in. So instead of solving for the differential equation part E, can we use the general form and just plug in the numbers? Well, m, I think, was what? 100, yes. And then 1 plus c to the k. What was the k value? Yeah, sorry, the negative k, so negative 0.001. The m was 100 times t. And yeah, I would have got the same thing, right? P equals to 100 over 1 plus c to the, and I think that is just negative 0.1 t. And once again, plug in 0, comma 10 to solve for c. So I don't want to do it again. I know it's the equation here that I've now highlighted and boxed in blue. Yay! Now, in question F here, it says, can you find the limit as t approaches to infinity? Well, I think you already know the answer to that, right? Looking at the graph, as t goes to infinity, yeah, it looks like it approaches 100. But can you actually now prove this with the equation? I think so, because I'm asking you now to take the limit as t approaches to infinity of 100 over 1 plus 9 to the negative 0.1 t. And when t goes to infinity, when I have to the negative infinity, that pretty much is 0. So that's just 100 over 1 plus 0, which is just 100. Makes total sense. Now, in part G, I'm asking you when will the bear population reach 50 bears? So when is t? So I want you to find t when the bear population is 50. And so yeah, all you need to do is plug it into the equation. 50 equals to 100. 1 plus 9 to the negative 0.1t. I guess we have to solve this. Okay, so 50 bracket 1 plus 9 to the 0.1 t equals to 100. I guess I can divide that by 50, so I get 1 plus 9 e to the negative 0.1 t equals to 2. And if I solve, I guess, yeah, what's that? 9 e to the negative 0.1 t equals to 1. I guess I can keep going. Yeah, I guess I can go. I don't like this, but oh well. That equals to 1/9. And then take ln on both sides. So negative 0.1 t equals to ln of 1/9. And then t just equals to ln of 1/9 all over negative 0.1. Calculator time. Calculator time. What do I get? Ln 1/9 divided by negative 0.1, 21.972. What are my units for time again? The units for time. They're not saying. Let's make it up then. Time is measured in years. So here we go. 1.972 years. Okay. Now, if you didn't want to do all that work algebraically, I guess you could just plug this into your graphing calculator or this one and solve too. That would be okay. Okay. Now, for part 8, it just says, when is the bear population growing the fastest? So if you look at the graph, the place where it's growing the fastest is probably where you have the highest or largest slope, probably right about here. So how do we find something where it's the largest slope or the maximum slope? Ooh, did you hear me say that? Maximum slope. Growing the fastest, maximum slope. Well, how do I find the max of the slope? I have to take the derivative of the slope and set that equal to 0 and solve. Yes, that whole business of finding max and mins. So I'm going to ask us to look at the equation dp dt again, and I think from part A that was 0.001p bracket 100 minus p. I'm going to ask you to multiply this out so that we don't have to use product rule. Ooh, 0.1p minus 0.001p squared. If that is my derivative and I want to maximize this, then I need to find the derivative of the derivative, which is the second derivative. And then the derivative of 0.1p would be 0.1. And don't just leave it 0.1. Remember, a lot of you did that in previous tests. This is 0.1 dp dt minus 0.002 p times dp dt. Remember, p is like the y value. So this is like implicit differentiation. Remember, we have to make this equal to 0, so I'm going to make this equal to 0, and I'm going to factor up dBdt, because then I have here 0.1 minus 0.002p, like this. And if I make that equal 0, then either dp dt equals to 0, which doesn't really help me, or 0.1 minus 0.002p equals to 0. That does help me, because I can solve for that now. 0.1 equals 0.002p. What is this equal to? Calculator time. 0.1 divided by 0.002. 50. It's growing the fastest when the population equals to 50, which just happens to be my answer to part G, so I guess it's growing the fastest when t equals to 21.972 years. Now, of course, I should have made my number line, but I know this is already going to be positive negative, so it's going to be the fastest. And this it does correspond to, yeah, when the graph equals to 50. Don't you love it when the picture matches the analytical algebra? I showed you, and I hope you do too, because that is the end of 7.3. Okay? Don't be afraid, all right? It does use partial fractions, but you can always just, plug it into the differential or the logistic equation if you want to. Just make sure you plug in the right things, and you are good to go. All right, that's it for 7.3.